behalf of RWTH, I'm really happy to see you here in person. Those many faces in one room, which we didn't have last year at least. I do remember us doing the first words in welcoming everyone, but it was in front of like cameras and all sorts of things. So it's much nicer in here. So I'm very happy to see you, especially welcome to those guests who came from far away, found your way to Aachen, into like the most western part of the country, and it's always worth it, isn't it?
Absolutely. No, it's really great. I only can echo what you said, Malte. Is 2 years ago we just reflected. We had this at the time still CKI, of course, and that was virtual, and that was good in terms of getting information across. But of course, it's not the same really looking into each other's eyes and then having a good conversation. And these random conversations about you are exploring and you say, well, how about this? And then you create new ideas. The creativity that emerges just by humans coming together and interacting is really, really great. So I'm very grateful for being here today. And thank you, Malte, for having us.
Yeah, thanks, Peter, for coming. I mean, you made the long way to Aachen. We had a lot of discussions this morning in our Hochschulrat, where you're part of, which we are very grateful for. And we were discussing the current situation for sure. Also the current situation since, I mean, RWTH is hit by the energy prices. Probably everyone is, and we have to cope with that kind of situation. But this is just a challenge for us. I mean, and this is especially why we're so happy to have you on board, because I truly believe that some of these really large challenges we are facing right now, you can on the one hand only solve by using deep tech, and on the other hand only in those kind of collaborations which we have. And it's not only the energy crisis, it's also a hunger crisis, so we need to find ways to feed our population and a lot more. And we are a basis for technology, we are a basis for talent, so this is what we can offer, but we always need collaborations that really bring those inventions which we have into innovations.
Yes. So this morning, I have to tell you, this was very interesting. So we had a very good conversation with the University of Aachen and then, of course, the rector. The interesting thing is that energy prices are going through the roof. And everybody really is struggling of how to contain them, right? Yeah. And then we had a discussion about, of course, what do you do for your budget next year? But then immediately you ask the question, what can you do sustainably in the long term in order to drive this down? So, for example, heat pumps, for example, intelligent grids, for example, intelligent buildings, for example, building digital twins of course, let's say, buildings, but then entire campuses. And that was the good conversation about, I think, Aachen has this, RWTH has this very unique position that you have self-help potential, we would say, in the capital market, right? Self-help potential in the way that you've got so many bright minds, and we get bright minds and great technology too, which if we bring this together, I think we can do a lot, and this is why we're here today.
Yeah, that's the thing, because it's not only RWTH, it's a company like Siemens, and I do remember this walking down memory lane for me a couple of years ago, sitting in this room and listening to some of your colleagues talking about how intelligent you can make buildings. And that was so impressive for me, because the world is always talking about Silicon Valley and all those companies which were out here. And then I listened to the talk and thought, this is what Silicon Valley should do. And honestly, what they do, they got a lot of money and they put people behind Excel sheets and they call it artificial intelligence, which is not. But you had some solutions for that, and that was impressive for me. So this is why I love the conversation, because I always get those ideas here.
We like that too. Thank you for that. Still, I would argue a lot is still rule-based, but Hermann probably is going to kill me now for that statement. But all the same is. You make a good point, because we try to be here today to bring a lot of different disciplines together, because we know innovation really happens if you have different people that think differently. So it's not just academics, it's company and startups, and it's not just Aachen, but also, of course, we have Alex today from Delft here. Last year we had KU Leuven here, and Hermann is from KU Leuven, and so I think it's really great. You mentioned it being in the western part of Germany. That means that you are opening up also to in other countries. And the way you live this is really, really, in my view, unique in the entire German university system. And Natasha knows it well. Would you agree? Yes? Yes.
Well, this is cool for us. So welcome also to especially those colleagues coming from Netherlands and Belgium. And this is what we really would love to live. And you just mentioned the open ecosystem. You mentioned the startups. This is something we built up here. So we are proud. We had 101 startup coming out of our university last year. However, this shouldn't be a closed shop. And this shouldn't be us. We are just the nucleus for technology and ideas and technology ideas and talent. So in that combination, if you put talent and technology together, you can create many good things. And but we are open for any kind of collaboration. This is why, for example, we just developed the platforms like a deep tap platform, but the business models are going to be done in our DigiHub, and when we need more talents, we go to the collective incubator where you're going to be tomorrow. And this should be open, because I truly believe only by being open we can change the world together.
Agreed. Well, look, we take 3 hours of your lifetime. Thank you for giving these 3 hours to us. I encourage all of you, do the most out of it, yeah? And really connect to your neighbor. Maybe you sit to somebody that you don't know, that you talk to, and these are the random conversations that you have. You generate ideas, indeed, of what we could do together. I would say the big challenge is 60%. 60% is really the amount of energy costs that have been increased. Do we find technologies in order to drive it down? Intelligent grids, hydrogen, intelligent buildings, everything. So I'm really looking forward to the conversation this afternoon. And maybe last point, last request from my end, just not make only networking connections, but really what could we do? Yeah, so a bias for action of what could be a next step, create new ideas, and then really get going. Because I like what you said, Malte, is we always look at the Silicon Valley. I tell you, I'm sick of it, because it's not true. A lot of great things are happening around us here, and sometimes we are just also not as good as telling the world what we do.
It's good to hear that, Peter. So, but I would love to say the same. I'm looking forward to the conversations this afternoon. I cannot. I'm so sad about that. Since switching around this conference, it really hit me, and I have to go to Berlin this afternoon because I have something which I couldn't push away. Yeah. So this is what's happening with me this time. I'm sorry for that. I would have loved to stay here and hear some of the newest ideas which you share. But I think I truly believe it's worth it. So for everyone, welcome today. Peter, thanks for coming. Siemens, all the colleagues, and I'm very glad you found your way, and I'm very much looking forward to what you are going to do and to hear about that, and yeah, to our collaboration also in the future.
Great.
Thank you very much.
Thank you so much. I think, yeah.
Gonna hand over to Yasmin, who's gonna be our master of ceremonies in this afternoon. So thanks again. Thank you very much.
Thank you for coming.
Thank you for coming.
Perfect. Thank you. All good. Thank you, Dr. Körte. Thank you, Professor Brettel, for kicking off our annual Siemens RIE conference here in Aachen. I am also very glad that so many of you followed our invitation to be here in person today. I would like to also welcome everyone joining online, virtually, and being actively part of this conference. Hello and welcome to everyone. As Professor Brettel already mentioned my name, I am Yasmin Zilt. I'm the new Siemens RIE manager here at RWTH Aachen, and I will guide you through the program today. And first, I would like to welcome also Dr. Stefanov from TU Delft. So we mentioned we are growing, expanding our network here, involving different countries, regions, which we are doing, but not only drawing the arc metaphorically, but actively connecting the different parts. And I'm really glad that he is here in person today. I heard it was a long way, even though it's very, very close, but 4 changes? 4 in total. How many kilometers is it? Yeah, so I think the public transportation here in the region could improve a bit, but thank you for being here and being part of our ecosystem. Yeah, without any further delay, I would like to welcome our first keynote speakers. We have the pleasure of having a tandem keynote on the topic Grids of the Future. Professor Dr. Albert Moser and Professor Dr. Stefan Niesen are here today to give us insights on the grids of the future. Professor Dr. Albert Moser, he is from the Institute High Voltage Equipment and Grids, Digitalization and Energy Economics, and he is the head of the Transmission Grids and Energy Economics. And Professor Niesen, he is from the Siemens AG, and he is the head of the technology field. Today's topic, sustainable energy and infrastructure, and he is also a professor at the Technical University of Darmstadt. So we have to mention that. I think he will mention it anyway. So we would also welcome you here to teach at our university. But I would like to welcome first Professor Moser to the stage, and then followed by Professor Niesen. I would say we can make a smooth transition and hand over later on to Professor Niesen. But first, please welcome Professor Moser.
Yeah, thank you very much for the introduction and also for the invitation to have a presentation, especially a tandem keynote. And it was quite easy for Stefan and me to separate the topics, because we are a little bit more specialized in the distribution system, like Stefan Niesen and I, as you have seen in my introduction. I'm more focusing on transmission systems and also on energy economics, also important part today nowadays when you look at prices, but we are talking now about grids. So grid of the future, so I have the pleasure to look into the glass bowl, to have a forecast, and there are so many forecasts available. What are the requirements for the grids? And that's what I want to start with, looking at the requirements. Fortunately, in Germany, we have an official forecast or an official glass bowl, and that is these are the data which are used by the German transmission system operators. They have to design a network, a future grid that can cope with these requirements. And I have collected two types of requirements. The first one, generation. The second one is more the load and storage part. And as you can see, it's not very new for all of you, but the figures are still impressive. Yeah, we have here a stack of different generation. Nowadays, today we have about 200 gigawatt. Yeah, about 100 gigawatt traditional conventional power plants, and the rest are renewables. And the part of the renewables will increase, and it will increase dramatically. You should look at the timeline, 2037. We already need a grid that can cope with 600 gigawatt of generation. Of course, not all the time, yeah, but we have to integrate it. And 2045, when we reach the climate neutrality in Germany, it's even a little bit more. What is important? What are the changes? I have marked here a dotted line. Below the dotted line, we have the traditional, what we call dispatchable units. You can turn on and off. And above the line, these are the volatile units. So it's more the weather that decides if there's a generation or if they don't generate electricity. But most important, also from the technical side, we have a switch from what we name synchronous generation, so from generators, synchronous generators, towards inverter interfaced generation units. And as you can see, the amount of inverter phase will increase dramatically. On the load side, I've also collected here some figures. I have not put in all the loads, the more what we call, let's say, flexible load and storages. And we see that on the mainly in the distribution grid, we see a strong increase of new loads, and all of these can be considered as flexible loads. We will have also an increase of storages, which are by definition flexible. And most of them comes, of course, from home battery storages, utility scale batteries, which we expect also in Germany, and the traditional pumped hydro. They will not change, so it will remain. We have some demand side management, more from the industry side, and on the household side, we have these electric vehicles, the power to heat pumps, electrolyzers, more large scale. So we have a huge amount of flexible loads. I will not focus on the dispatch. It could be an additional topic. I will focus on what is the consequence for the grid. Yeah? And this is actually my next slide. I have collected the main challenges. What is required? We have, although most of these new loads and generation are in the distribution system, there is still a need for increased transmission capacity. Because most of the generation is in the north, yeah, where we have windy region and so on, and most of the load is still here in the west and in the south of Germany. Yeah. We need to integrate also the offshore windmills and also offshore networks in the North Sea and the Baltic Sea, and we have an increased need for north-south transmission. Yeah. On the other side, we need an integration of flexible loads and storages into the markets, but also into the ancillary services, so congestion management, voltage control, frequency control, and so on, but I will not focus on this here. And we have a need, sorry to say this as an electrical engineer, for reactive power. Yeah? It's not the active power, it's the reactive power, because all the traditional power plants did not only provide power, but also electrical power, reactive power, which is needed to keep the voltage levels in all levels. Yeah? And we also need not only to keep the voltage a steady state, we have also to cope with the volatility. Yeah, volatility in the generation leads to a volatility in voltages, and you have to control this somehow with a flexible reactive power provision. And we need to keep the system stable, also inertia, because the rotating masses of the traditional power plants have provided inertia for in case of a mismatch. When there's a mismatch in power, yeah, then we have a deviation of frequency, and the inertia provided a stabilization here. And with the inverter interface, so far we don't have it. We need solutions for it, and also for the short circuit power, which means when we have a voltage drop, we have to make sure that the voltage drop is not too steep and too deep, so that after clearing of, for example, of a short circuit, the voltage recovers again and keeps the system stable. So what is needed? It's not only digitalization, that's also required, and control, very important, but we need, at least on the transmission side, also new devices. Most of them are based on power electronics. Yeah, most of them are based on power electronics. We need these devices for load flow control, for example, to bypass congestions and use lines which are not so heavily loaded. Yeah. In order to increase transmission capacity, HVDC technology is one of the most important devices we will integrate into our network. It's not only Germany, I think it's worldwide, also to interconnect beyond the North Sea and the Baltic Sea. And we need innovation in system operation. I have named this reactive system operation. What does it mean? In the past, we kept our security criteria, that is the so-called N-1 criteria, which makes sure that when a line trips, the system is still stable. So we did a lot of preventive operations. So in expectation, a line could trip, but this is very costly. If you are very fast with the control, you can react right after the fault occurs. So immediately after, very fast. And this is what we call reactive system operation. And this, of course, gives you more capacity in the transmission system and makes the operation quite cheaper. So we need also innovation in power system control. We also need devices to provide reactive power, inertia, and short circuit power. All of them are more or less power electronics based. So I name the STATCOM, the static compensator, which can dynamically maintain the voltage level, or synchronous condenser, which is more a traditional device. To provide inertia, we definitely need grid forming capability for converters, which is a huge step forward for inverter interfaced generation units. Even if you have a so-called STATCOM with grid forming capability, you can provide inertia if you add an additional storage to the STATCOM. And both devices, the STATCOM, the synchronous condenser, and so on, can also provide what we call short circuit power. My last comment, because we are talking a lot about decentralization and microgrids and decentral control, but we have also an opposite movement, opposite development outside. We have also, in addition, not to replace a decentral system design, but on top of it, we have a development towards a global transition system in order to transport all the different renewable energy across continents. Yeah, for example, this is a study by SIGRE, a well-known engineering organization in the high voltage area. I just want to add it. As you can see, Europe is not anymore in the center. If we design a global system, the center obviously is in Asia. Yeah, and we could be happy that we are still in a loop, that we are in a mesh. Yeah, but the center, the electricity center of the future is obviously in Asia. Yeah, thank you very much. This is my short keynote, and I'd like to hand over to Stefan.
Yeah, Albert Moser in his speech has mentioned the steep increase of flexible consumers and storages, and obviously most of them will be connected on the distribution level to distribution grids, which is why we said that I would be speaking on the distribution grids in our tandem speech. And another reason is that RWTH Aachen, in particular Albert Moser and also Professor Monti, are together with us partners in the largest publicly funded research project where Siemens has the consortium lead. It's the Copernicus and SURE project. So this project spans over 10 years, and we are currently in year 6. And together with an ecosystem of a total of 21 project partners, it is our ambition to break up the proportionality between more renewables and more heat pumps, chargers, and so on, and the installation of new grid primary technology. And so that you don't have to put next to every windmill also another new transformer and switchgear and so on. So in my speech, I want to present you some ideas on how we can do this. So spoiler, just in short, in a few words, we use sensors, we use communication, we use central, decentral, and cloud computing, and as Albert already mentioned, power electronics for an increasingly intelligent operation of the grid in symbiosis with the grid users. In order to increase the suspense for the next 9 minutes, the grid operators in our consortium, they have authorized me to formulate the following question. Would it be possible to, using today's available grid capacity, transmit and supply twice as much energy? So you might be astonished. We believe that the answer is actually yes, but under a few conditions. Let me go through those conditions and explain how we work on those in the project together with our partners. So one precondition is that the grids need to be monitored better than today, Because the more accurately the grid operators, and I speak about the distribution grid operators, the more accurately the grid operators know voltage and current in their grids, and the better they are at predicting them, the less unnecessary safety margins they have to take. And so my team at Siemens and also a team at the University of Erlangen are developing technologies to monitor grids effectively. And the challenge here is that even today, sensor and communication technology with the required reliability for public supply is actually too expensive in order to be deployed everywhere in the grid. So our ambition, therefore, is to develop methods to get most accurate estimation of the grid state using a minimum number of sensors, communication, and infrastructure. And by choosing the best placements for them, and then to intelligently interpret the measurements. So Professor Monti, director of RWTH's Institute for the Automation of Complex Energy Systems, and his team are developing a low-cost measurement device and aim to even further reduce the costs, as you see below. Something has happened to the PowerPoint version, sorry for that. As you could see below, you would read that there is an edge device and a connection to actually a cloud system that allows to interpret the measurements in the cloud, which would then further reduce the costs. And then, building on such measurements and such assessments of the grid state. Now the presentation is even stalled. Now it works. So once we have those assessments of the grid state, then control and telecontrol technology allows to determine the best switching operations and to execute them. Actually, the possibility of telecontrol operations might sound trivial to you. Yeah, everyone has a remote control for TV at home. However, today in distribution grids, telecontrol technology is not at all a common practice. Therefore, a further prerequisite is the improvement of grid control and telecontrol technology. For instance, substations are a non-negligible cost factor, and their flawless functioning is a prerequisite for a secure electricity supply. However, the concern for the security of supply should not lead to unnecessarily early replacements of such expensive components that are subject to wear. So our project partner, Hitachi, for instance, is developing an improved method to assess the state of health of a substation. Also in the project, there is a contribution from Technical University Ilmenau showing us how innovative concepts are ready to go to the edge of the technologically feasible. So there, they develop a method that automatically detects if parts of the grid can be operated as an electrical island. And this requires then a balance between generation and consumption, of course, in the island within the subgrid. And it also requires a sufficient number of measurement points in order to control it and disconnection points to really go into the islanding mode. But why would anyone want to run such a grid in an island mode? Well, the option, at least the option to run it in an island mode, makes a region robust against any disturbances on the superior grid level. So, for the sake of timing, I will skip the two further activities you see on the right-hand side on this slide and move right on to the next prerequisite. So, control and telecontrol technology can make an impact if the grid assets are able to adapt their behavior flexibly. So, as already mentioned by Albert Moser, power electronics and the special application DC technology can greatly contribute to the necessary flexibility in the grids. So, wind and PV generators, hydrogen electrolyzers, battery storages, and charging infrastructure have one thing in common. They are all using DC. And these are then connected to the public AC grid via inverters. And while the conventional power plants are shut down, as Albert mentioned before, that have been ensuring the dynamic stability, our project partner, Maschinenfabrik Rheinhausen, investigates how in the future inverters can take over the stabilizing function as mentioned by Albert Moser before. And Albert Moser's institute, IAEW, contributes also interesting research on a meshed operation of distribution grids. So usually distribution grids are operated with open rings. So usually this would be open, this switch here, right? Which often is good, but then sometimes it can be better to close it. And so in his research, he develops and evaluates different alternative operation modes, simulating them for a wide range of distribution grids all over Germany, and showing that actually, although from a technical point of view, MVDC technology would be best, but from an economical point of view, the best compromise is actually meshing using AC switches. So, the more distribution grids contribute to the overall system stability, the more important it becomes to have an increasingly close coupling between the distribution grids and the transmission grids, because the stability will increasingly come from down below. And a key element of this coupling is an aggregation of stabilizing contributions from assets connected to the distribution grid so that it can be activated by the transmission grid operator. And then we work on how it can be integrated in the control process together with our project partner at TU Dortmund. And last but not least, the flexibility of the consumers will be an increasingly important column, as mentioned by Albert before. And so in the Ensure project, together with the partners, we investigate the practical use of flexibility originating from charging processes, heat pumps, and industrial flexible load. So I am aware that this was a lot of information in a short time, but my main message actually is, and that I wanted to bring across, is that the energy turnaround, the Energiewende, is only possible with innovation in the grids. And there is reason to be optimistic that today's grids are actually able to supply twice as much energy. Obviously, if you build a windmill in a place where never any consumer has been, then you need to build a line there. That's not a question. But a lot of the consumers already have connections today. And you might have felt it or heard it between the lines. We really like to innovate on ecosystems together with our partners, and we really highly appreciate the cooperation with the excellent research institutes at RWTH Aachen. Thank you for your interest.
Thank you, Professor Moser and Professor Niesen. Wait, I'm gonna skip a few slides, and I would like to ask you both back to the stage for a couple of questions. I hope our audience has questions for Professor Moser or Professor Niesen. Are there any? Perfect. Do we have? Oh no, we don't need a exactly. Perfect.
So Professor Moser, you showed 3 times increase in capacity. You talked about, Stefan, about doubling on the grid. So how much do we need? Do we need doubling? Do we need a threefold? What is it?
So we distinguish, of course, between power and electricity or energy. Looking at the power, of course, we have an increase in capacity, but it's not at the same time. Yeah? Actually, we build 2 systems. When there's wind and sun, we use it. And if there's no wind and sun, we use whatever the gas-fired station, of course, green gas in the future, and batteries, and so on. But with respect to energy, we expect about double the amount. Yeah, today we have about 500 terawatt hours in Germany, but if we have all these electrolyzers, all the electrical vehicles, so it's twice the amount of today. That's what the forecasts say. Yeah.
Perfect. Thank you.
Yeah, true.
One more question before we continue. No, then I would say we can continue. Thank you very much. Yeah, I think I will just, before it rolls down and breaks. Here we go. Thank you. All right, so we have gained insights into the grids of the future. So now, logically, we need to know about the buildings of the future by Professor Dirk Müller from E.ON ERG Energy Research Center and the Institute for Energy Efficient Buildings and Indoor Climate. Just handing over. Thank you for being here.
Yeah, thank you very much. It's a pleasure to be here today and to speak about buildings. And I got the same title as my colleagues, Building of the Future. And of course, it's always difficult to speak about the future, but because who knows how the future will really look like. So we only can make estimations of the future. But in this case, actually, it's very easy to give an estimation because I immediately can show you how the building of the future will look like. It will look like, it will look like this. Because we already know the building of the future, because it will exactly look like the building we have today already, because we use our buildings for maybe 80 years. So when we think about buildings in 30 years, it will be mainly the buildings we already know and we already use. And every building is part of a city environment. And the thing what is now changing is that we more and more see a building as an active part of a city environment and the city energy system. So this will be one of the main change, not the change of the building envelope itself. And first, I would like to start with very easy remarks. And when we look at our well-known triangle for the energy world, then we know, of course, we have three pillars we always have to watch. And the first pillar is economy of the electricity and all energy supply we have. And in the past, when we look back maybe 30 years, economy of energy was the most important topic because we need cheap energy supply. And we look back for the last 10 years, of course, then we have a different discussion. More and more renewable energy is in our focus, and we know we have to be more sustainable. So the environment plays a very important role in all of our decisions. And when we look 1 year back, there was a big change in policy in Germany that really everything had been more or less put on renewable energy generation and energy efficiency. But after the war caused by Russia, the situation has completely changed, and now we are purely focused on supply security because we realize we cannot rely on our gas supplies anymore, and we have to be very careful how to use our energy now and where to save energy as fast as possible. And we look at the building part, then of course there's hope because we also have three pillars we can use in the future. One pillar is efficiency of our buildings. And when we look at efficiency, we can gain efficiency by better energy system engineering in buildings. We can go to less losses. We can use new technologies. And of course, civil engineering. A very important part. We need a lot of retrofit work on our existing building stock. We are already able to build very good new buildings when it comes down to civil engineering problems. But we need more. And one possibility is, of course, using external renewable energy. We can connect our buildings to heating networks. We can use different renewable gases, as already mentioned. Some people even think we will see H2 at building blocks. I'm not really sure that this will really happen. But, for example, also biogas will be an important part in the future for our energy supply of buildings. And of course, buildings offer a lot of local renewable energy. So we can have solar heat, we can PV installations in our buildings, we can use geothermal heat and also ambient air. When we combine it with heat pump technology, is a very important source for our future energy supply. So now look a little bit closer at this triangle, and then of course we can decide how to fill the 3 blocks. And if I just put like one topic in every block, I would say on the first block, when we look at what has to be done in terms of efficiency, then we need a different process for refurbishment of buildings. It has to be industrialized in a very different way. That's not my special topic, so I just want to mention it. But I will focus on the 2 topics we have on the bottom. One is like district heating networks of the future, and the other part, of course, is heat pump technology, because this is a part that's very important and running up now very impressively in the market. And everything has to be related to city district solutions, so it doesn't make much sense to look at a single building alone. We always have to think about the grid, of course, the electrical grid, and we have to think about all other buildings in the surrounding of our buildings. My first look will be in the area of heat pumps, and there I think it's an interesting discussion. What does it actually mean when we really convert our buildings to heat pumps? We try to calculate what is actually the peak power demand just for heating buildings, commercial and residential buildings today, which is delivered by the gas grid. And it's an amazing number from my point of view. Our calculations must be something like 275 gigawatts on power. And the moment actually we need this power is a very cold day in the winter with no sun and maybe no wind. That's the situation for the peak power demand. And now we can calculate what does it actually mean in electricity. If I'm optimistic, I would say, okay, everything is converted to heat pumps, and then maybe we have a coefficient of performance for 2. That means 1 kilowatt hour electricity gives us 2 kilowatt hours heat. Could be even better, a CO2 of 2.6, and these numbers have been used by many studies. But actually, when we have a more realistic build, we can think about a day temperature below -10, then actually a COP of a heat pump would be very close to 1, because it's more or less direct electrical heating. And then we are back to 275 gigawatts. So that's far above the numbers you showed. And we have to be careful to watch this very closely. Even if we would start a big retrofit process and all buildings which are now linked to the gas grid will be at least renovated and get a new exterior wall insulation of 12 centimeters, it would still be a large number, even if we compared with a heat pump with a COP of 2.6, because it's exactly in the same range of our today's peak power situation. So this is serious because we also add electricity for mobility. So this will add on in this picture, and it's maybe not an energy problem, as you mentioned, is mainly a peak power problem from my point of view we have to solve. So now look at the area of district heating as a second topic. And also in district heating, some people think it's the most boring topic in the world because it's just pipes we have to put on the ground. But actually in district heating, many things are changing right now because we are going from our conventional system, which always starts at a very high temperature, above 100 degrees, and goes actually down to the distribution network, to the demand side in the building to 60 degrees. This is changing now rapidly because we see already the first grids running on lower temperatures between 80 and 90 degrees because it makes it much easier to integrate solar energy, for example, directly in a heating grid solution. But the next big step will be we actually go to cold grids. This is the grids of 5th generation for district heating. And cold grids have many advantages and some, of course, disadvantages. One of the main advantages, every kind of waste heat can be integrated immediately. So you can integrate waste heat from data center at any temperature level. Can be an old data center, maybe by 20 degrees, newer data center up to 40 or 50 degrees even. You can integrate geothermal very easily, and also ambient air-powered heat pump can be integrated easily without losing too much efficiency. The distribution is then handled by a very easy pipe system. You don't even need insulation of the pipe system because the soil is actually working like a buffer. No? So it's nothing you have to be scared of, no, it's an advantage. But in every building, you have to install more technology. At least you need a heat pump in every building connected to the grid. No? And additionally, all buildings that need cooling, and this will be more and more buildings in the future needing cooling anyway, have to integrate a chiller machine as well. So what does it mean for our future energy solutions? We have maybe a cold grid line going in the future here in our campus around from building to building. And in every building, we have a heat pump and we have a chiller machine. And when we have good insulated buildings, some buildings, depending on the use, will use cooling more or less all over the year. And some buildings will still need a lot of heating, especially residential buildings will be always focused on heating. So we can have very different types of operation in this grid. For example, we can have a building like this. Part of the building, depending on sun is shining on one side, the other side is on the shade. Part of the building will need cooling. Another part of the building will need heating. So you can just circle around heating and cooling. So it's a very efficient operation between heat pump and chiller technology in one building. But also we can have a situation that we have one building that mainly needs heating and another building that mainly needs cooling. And then actually the grid will be used to exchange energy between two buildings or any kind of number of buildings, just using the grid as a backbone for energy transport. And of course, we can have a situation in the grid where most of the buildings will need heating power. Then you need your central energy center to supply enough heat in the cold grid in order to make sure that all buildings can be supplied by the internal heat pumps. These solutions have this big advantage that we can exchange energy inside a building and between buildings, and also has a big advantage that we don't have to install, for example, outdoor heat pump or chiller units in every building. So in dense areas, you also get no noise problems, as will be as quiet as we have it today. So my last focus is on district solutions, and that's maybe the most complex part for all of us right now, and I think we have to learn on practice. So we really have to go in this kind of, sometimes from a scientific point of view, very annoying projects where you have a lot of practical problems. And we're actually doing this with many partners now for some years. And just 3 examples for you. One example is from Berlin. It's like a big retrofit process for the building you can see on the left side. And actually the building, the structure of the building will be reused completely. So it's a concrete structure that is still in good shape. And we will add some new buildings, and this will be a fully electric solution. And this has been decided before anyone had the feeling that actually natural gas would be not supplied anymore in the way we are used to it. But this was very early a decision to go to electric solution, also to integrate battery storage technology in one of this building to have a very flexible building operation. Second project is actually the first Reallabor, the Energiewende. This is like a large-scale project financed by the German government. It's a total budget of around 45 million for one project. And actually, we look at 3 different sites, one urban district, one new build, and one industrial district. And we try to find good solutions fitting to the loads we have in these buildings and in these building areas. We have a high-density energy sink on the one side. We have a potential for renewable energy, also wind for a new district. And we have also one solution considering hydrogen as an energy carrier, especially in combination with industry. So all of them will be built in practice or on the way of building them in practice with all the difficulties, of course, we get. But the important part is we only have one data platform running for all of them. And that's, I think, something important. This kind of data platforms providing control and providing service for these highly distributed energy solutions, they will become more and more important. The second Reallabor der Energiewende is Transurban NRW. It's a big local project here in North Rhine-Westphalia, and this addresses exactly this cold district heating system, so advanced district heating solutions. And we are very happy that we can be part of this consortium, building up 4 new sites using this kind of new district heating systems. And also we can develop a lot of new planning tools that can be used to be faster in practice. But also regarding regulation, many things have to be changed and have to be addressed in this Reallabore. So it's a big exchange with our ministry as well. When we look at this sites, we are looking at for Transurban NRW. It's quite huge. We have Shamrock Park and Herne, and this is like residential and non-residential applications. Interesting when we look at heating and cooling, it's a factor of 2. And then we have sites, for example, like Erkrath, Düsseldorf, Terrassen. Then actually it's more up to 1 to 4 when we look at heating and cooling. And that also means for the application of cold grids, the first part in Shamrock Park, very easy to be economically successful. Düsseldorf Terrassen, you have to calculate more carefully if this is a good solution or not. And also you have to integrate some estimations for the future cooling demand. But especially when you add new buildings, cooling demand for the summer season will for sure also in the residential part will be increased. Again, in this project, of course, anything is related to one platform, organizing the full set of systems you have to integrate. So a lot of decentralized technologies, but also some information from the electrical grid that has to be integrated, and then you need something like a platform. And it's a big word, and everyone is working on platform solutions. Also Siemens is working on platform solutions. But on the other hand, we know the final customers, they would like to have something which is open enough, to be flexible enough to give different companies access to this kind of infrastructure. So I think it has to be designed very carefully, and together with our partner from ACS, Antonello Monti, we have designed this platform based on a European project, FiWare, where we have enter different protocols. We can use different kind of IoT agents that are, from my point of view, it's really enabling technology what we need for this kind of energy data structures. Then we have the typical design of a content broker, and then we can provide services. And in this sense, for example, from my point of view, we have some classical services like visualization, but also we can have some newer services like control. So like model predictive control can be really think as a service, and doesn't have to be like part of the first solution you build in the building, for example. And of course, it has to be sure in order to be able to be successful. So buildings of the future, what do we learn from this presentation? It's like they are already built today, so there will be not a lot of new buildings in the future, but they have to be flexible. Many systems will be data-driven, and of course they have to be user-centric. So we have to be very close to the human being, and we have to design the control system of the building that is really following the demand of the user. That's my presentation for today. So thank you very much for listening.
Thank you, Mr. Müller. I would say due to the time, we could discuss any further questions in our networking session. So I would suggest to continue. Thank you very much for the insightful presentation. And yeah, let's continue with the next point. Thank you.
Thank you.
All right, so Pitch Your PhD. This is a new program point that we added this year. By we, I mean Siemens and here our university. We did invite doctoral candidates to apply to get the chance to pitch their research project here in front of you. And by pitch, I mean to introduce what they are researching on. And yeah, we have chosen 3 candidates to give us a short pitch. I will just repeat the rules one more time. So the pitch is going to be 3 minutes long, and then we will have time for 1 or 2 questions by our jury. And our jury consists of Dr. Eckert, Dr. Körte, we have Professor Niesen here, and also Dr. Suplinski will be part of the jury. So you will decide later on the winning pitch, and by winning, I mean prize money in, what's 3,000 euro? Yeah, so 3,000 euro, very nice little award. And I would say without any further delay, we can start with the first pitch by Paul Maximilian Röhrig. Please come to the stage. He will tell us about using machine learning to learn optimal operating strategies for grid-connected buildings. No?
No. It's a different topic. But no problem.
Okay, I'm sorry.
Yeah,
It's a new pitch.
I
I forgot the challenge on pitch a new research project you probably only worked like a few years on. Sorry. Please introduce us your topic by yourself. And also a little reminder, please do look in this direction so we also involve our virtual guests. Okay, here you go. Sorry for that. Good luck.
Okay. Does it work? Okay, perfect. I'm glad to be here and presentate my PhD topic, Analysis of Exogenous Influence Factors on a Robust Transformation Pathway on Municipal Energy Supply System. To better understand my topic, you need to understand the challenges. We are facing in the next coming decade the biggest challenge, the achievement of climate neutrality. In Germany, the building sector produced 28% of all emission. 40% of them will be created by the energy supply of buildings. This can split up in the field of electricity, heating and cooling. So we need to restructure our energy supply. There are different measurements how we can do this on the buildings level to create zero carbon emission buildings. The first thing what you can do, it's an increase or a decrease of the energy consumption by doing refurbishment. The second thing, it's an increase of share of renewables by putting PV roof photovoltaic system on the roof. And the third thing, what you can do is switching from fossil emitting technology to alternatives. All of these technologies or measurements depend on each other and also on the higher level, the so-called municipal energy system. This provides the grid of heat, gas and electricity. So to create a reasonable concept, you also need to implement this independencies between these measurements and the levels. The decisions will be also influenced by some factors like the CO2 price, the commodity price, the regulation, or the availability of resources. So to create a robust decision under these uncertainties, you need to understand what are non-regret decisions and avoid stranded investments. Up to here, it was easy, but I don't want to create a greenfield approach. I want to transform existing municipal energy systems that they can reach the climate neutrality in the next 22 years. So to do this, we need to answer the question, what do they, when, where? To do this, I will define some interim targets which are a guideline what they can do to reach this target. This brings a high path dependency in the decision, and also these targets are subject of the time limitation. So you can't do unlimited changes in one step, and all the steps need some time. The addresses of this work are stakeholder of the energy policy and energy consumption, which need a better understanding of the system and also a tool which can transform the system. The goal of my work is to create a method for developing strategic transforming pathways for municipal energy systems that they reach the climate neutrality. Thank you for your attention.
Introducing us your topic and not a topic that I chose or maybe someone else's research topic. Do we have questions? I think I can use this mic for the questions. One or two. Professor Niesen, yeah. I think you can just use your your headphone. Thanks.
Thank you for the pitch. Could you specify a little more where do you want to put the emphasis of your work?
Yes,
Should it
of
be
course.
in the developing of the method, in the analysis, and the practical application?
Yeah.
Where do you want to focus?
Yeah. My focus will to create a method which use a bottom-up strategy of how buildings can transform under the exogenous influence factor of the grid or some other factors like the price. And what are the limits of this transformation and one can which transform in the future.
Thank you.
One more question, if there is any question. Yeah, let me get, maybe you could help me to pass the mic. Thank you.
Thank you for your pitch. What do you understand under climate neutrality? Because I think, especially in the building sector, it isn't possible to achieve.
Yeah, I would totally agree with this point. But on the other hand, we need a target what we want to reach. And it's to emit lower emissions than today. And the way to this, it's for me the climate neutrality. So we need to compensate more or less some of the emissions in the end, but we set a little bit higher targets than possible for this.
Thank you. Thank you, Max.
Okay.
I would continue with the next pitch. This you can, oh yeah. So Clemens Schumann is up for the next pitch. Please go ahead, I will stop the 3 minutes.
All right. Thank you for having me. And welcome to my presentation on the topic analyzing the effects of a nationwide energy sharing rollout. In order to encompass all end customers in the energy transition, the European Union has introduced energy sharing. In energy sharing, end customers and small and medium-sized enterprises can exchange electricity among each others. To do so and to increase the self-sufficiency and the social welfare of the community, the end customers and participants use their flexibility, for example, from battery storages, electric vehicles or heat pumps, to balance load and generation locally. This leads to effects which are on the one hand side economically, as we can see here, that the utility, the electricity bought from the utility is reduced and the electricity fed into the grid is reduced and replaced by energy which is shared. On the other side, it can have also an impact on the distribution network utilization, for example, by balancing load and generation locally in low voltage networks, which then leads to reduced power flow in the medium voltage. All in all, energy sharing needs to be introduced into the national legislation by national policymakers who need information about those effects which originate in the flexibility operation. If we have a beneficial frame for energy sharing in the future, we may have also a rollout of energy sharing which is nationwide. In a nation, for example in Germany, we have a very heterogeneous regional division. For example, in the building stock, the distribution network types, and also the installed assets. For example, PV systems are more in the southern Germany, wind power plants in northern Germany. And this leads to several impacts of energy sharing. And to find an energy sharing design which is the best for all of those region types, but also for the overall energy system, the policymakers, but also regulators and platform operators who need to perform energy sharing at the end. We need information about the effects in all those systems. Therefore, the research question of my topic is which effects emerge from a nationwide energy sharing rollout. And I derived 3 research questions which focus on the topics distribution grid utilization, the topic of the economic impact of energy sharing, and how does energy sharing designs, for example, the spatial design, in which region can we share electricity, or the regulatory design impact the trade and the effects. Stakeholders, as I said, policymakers, regulators, but also platform operators, and the research target of my thesis is thus determining the effects of different spatial and regulatory designs of energy sharing. That's it from my side. Thank you for your attention, and I'm happy to answer your questions now.
Are there any questions? That was perfectly 3 minutes. Thank you, Clemens. There, on your side, Christina. Thank you.
Thank you so much for your presentation. Just a little question about the economics. You will create a lot of micro contracts of selling and buying energy. How to handle them?
Yeah, that's indeed a problem that I'm not directly solving in my thesis, but usually you can, on the one hand side, use peer-to-peer like in blockchains, but you can also use centralized markets for market areas, so that if we had a energy sharing community in a part of Aachen, then all can bid on a market platform, which is for this region centralized, to reduce the amount of bids. And then we have a high demand on ITC, on communication technology, to provide the possibility to communicate and to bid and to have all those contracts.
One last question. Again, on your side. There, last row. Thank you.
Yeah, thanks for the pitch. And I have a question regarding the detail of your model. So how detailed are you going to model the different districts?
Yeah, so as we can see, Germany is quite large and has quite many regions that we need to model, but we can define certain types. So what I'm doing is I cluster all the regions in Germany, and then I'm going down to the building level and simulate each building and the trade between those buildings in each region on a quarter-hourly basis, so that I'm modeling each technology in the building, in each building in some of the regions in Germany.
Cool. Thank you very much. You can take over. Thank you, Clemens. And our last pitch for today, I would like to invite Philip Joffel to the stage. Here you go. Thank you.
Thank you very much for the introduction. I'm Philip. Good afternoon from my side. And I don't think I need to tell you that we need to reduce our energy consumption and CO2 emissions. And in the building sector, one way to do this is by the implementation of model predictive control, as Professor Müller already told us. Model predictive control considers the forecasts for weather, occupancy, and also energy prices to find the optimal control decision for a building. By doing so, model predictive control exploits storages like batteries and the thermal inertia of the building. And the core of model predictive control is a mathematical model to predict the future behavior of the building. This core is also its drawback, because in contrast to the automotive industry, where, for example, one model is applied to 1,000 cars, so it's worth the modeling effort, buildings are highly unique. So we have a high individual modeling effort, which prevents wide-scale commercial application. So the question is, how can we achieve this? And my PhD thesis aims directly at this. By providing an automated workflow to generate model predictive controllers based on machine learning. I directly use machine learning to identify the building behavior based on monitoring data, and then reformulate those machine learning models into highly efficient optimization problems. Once these models or this controller is applied, we can also consider online learning by just retraining our controller models with new data again and again to improve our performance and also adapt to changing environmental conditions. And to show you that all of this really works, I present some promising results from our hardware-in-the-loop test bench, where we applied a controller on a real-life heat pump, which is placed inside a climate chamber and coupled it to a very detailed simulation model of a building. And what we see is that the controller actually managed to keep the indoor temperature right between the comfort boundaries, so no user will complain. and the heat pump just delivers the right amount of energy in the right time to ensure an efficient operation. Furthermore, of course, with slightly adaptations of the controller, we can, for example, increase the self-consumption of our PV plant or provide grid flexibility services. So, in summary, my contribution for energy reduction and CO2 reduction in the building sector is the optimized implementation of efficient predictive controllers for buildings. Thank you a lot.
Thank you. Thank you for your pitch, Philip. Questions?
I'm interested in what are your input data and how do you get them? Are they available right now or?
Yeah, of course, it's not possible for a just new build building, so we need to monitor the building for a couple of weeks, and yeah, then we basically need any data we want. So of course we need to know what are our inputs and monitor these inputs, like for example the flow temperature, set temperature of a heat pump. We need to know what to control, so the room temperature, for example, and of course we need to track the weather conditions, so to learn how the building react to weather. And of course, in the best case, we have also like an outlook schedule for the room to just learn how user behavior will influence or the whole system. So yeah, the more the better, of course.
Thank you.
Thank you, Niels. Any last question? Yeah, over there.
Same question, but just for the other side of the equation, what are the actuators that you use?
It depends. So whatever is there. So basically, if there are subsystem controllers, for example, for a heat pump, which controls the flow temperature, then we can also control this. Oh, there are no backup slides. But yeah, we actually managed, for example, to directly control a heat pump via its compressor speed. But it was also possible to just learn the behavior of the set temperature or valve positions or something. So we can basically control anything, at least if we can measure it.
Thank you.
Thanks.
Thank you, Philip. Okay. Thanks a lot to all our pitchers. You can sit down again. Thank you so much for applying, taking the chance to pitch your research topic here. Our jury has some time to decide, because now we are continuing with our last program point for today. I'm going to put this down. Our panel discussion, and after gaining more insights into the buildings and the grids of the future, now we want to combine both and see how they can interact intelligently. And for the panel discussion, I would love to invite our moderator. He's here, Niels. Welcome to the stage. So Niels is a team lead of distributed flexibility, also at the IAEW Institute, and he will host our panel discussion today, also introduce our panelists, and I would hand over to you.
Thank you, Jasmin. Also welcome from my side. I mean, the introduction was already done. So yeah, I shouldn't talk a bit about my person now, so let me introduce you to the panel. And I'm very happy to share the stage today with experts like Alex from TU Delft, from Siemens, and also from RWTH Aachen. And yeah, I look forward, and I hope you are doing as well, to inspiring contributions and lively discussions on these questions of how can buildings and grids interact intelligently. Before we start, I want to make one remark to the format of this. I would like to have the discussion here on stage. If you have any question that comes up during this speech here, I would ask you to keep it in mind and raise it at the end of the speech or during our networking, since time is scarce for our discussion today. So let's start, and before we start with the panel, I would like to give you a short motivation and a justification why this question of how can buildings and grids interact intelligently is so important. And I mean, we heard that already with the keynote speeches and also in the PhD pitches. And I want to summarize a bit that. And what we heard from all of them is that there is an imperative of technical transformation, but also infrastructure transformation. We heard doubling energy consumption in the electricity sector, and probably the need for grid expansion, grid reinforcement. But also, towards such a renewable energy system, there's a societal challenge for every one of us, for the industry, for the economy itself. And we already heard that the structure of the energy system will also change radically. In the old energy system, we could speak of a mostly central system with large supply chain. And in the new energy world, with the energy transition, as you can see in the picture, it will be more fractured and more complex. There was this topic of decentralization, and we heard already it's not all decentralized, but the unidirectional energy flows we saw in the past will probably be more bidirectional. And that can be on a national scale, but also on a local scale, and probably this pyramid you can see will be put upwards down here, and we will have a different system in the future. And the need for flexibility can be highlighted in this. So what we see here is what we call the energy heartbeat for Germany, which shows the picture of demand and production over a day here. And what we can see, we have peaks and valleys in this picture. And the problem we see is that production and consumption is an imbalance on a spatial scale, but also in a timely scale. And this is also emphasized for the future. So if we compare today to the future, we will have 5 times as high, at least 5 times as high peaks and valleys here. And that picture is from, I think we made it in 2012, 13. Now the new, with the numbers from then, if we look now at the picture, probably it's 5 times higher now. And yeah, there we see that it is evident that we need flexibility. And this flexibility can be used for the nationwide system or for local systems. And we also heard that there is the need for flexibility because we want to prevent grid expansion, because it will come with costs. And that is why it is so important to talk about the flexibility, which is probably mainly on the building level in the future. And yeah, I'm very happy to and glad to discuss this question now with the panel. And person per person, I would invite you, please, to come on stage. I'll tell you a bit about the bio of the speakers, and then we'll start. So, first of all, our special guest today, Alex Stefanov from TU Delft. Please come on stage and welcome. You can sit here. All right, thank you. So, Alex is assistant professor of Intelligent Electrical Energy Systems at the Faculty of Electrical Engineering and Computer Science at TU Delft. Yep. He holds the registered professional title of Chartered Engineer from the Institution of Engineering of Ireland. And you've worked in Ireland a lot. Your previous workstations were at Novogrid and ESP Networks, where he worked on manifold aspects of distribution system operation, so looking at power grids and the distribution there. And also in Ireland, he made his PhD and a postdoc at the University College of Dublin, where his research focused on cybersecurity for power grid, especially in smart grid environment. Yep. Welcome, Alex.
Yeah, thank you very much.
The second is from Siemens, which is Dr. Adam Slupinski. Welcome. Yes, hello. And I'm very happy to have you here since I think originally planned was Dr. Schwan, who is ill, unfortunately, today. So we're very happy that you are here for him today. And I'll give you a short introduction to Adam. He's head of distribution and decentral systems at Siemens. And previously, he worked at ABB AG in the power consulting unit in Mannheim with focus on power quality and transmission system planning. And before that, at Forschungsgemeinschaft für elektrische Anlagen und Stromwirtschaft, FGH in Mannheim and also in Aachen. And I'm very happy that you're coming back to your alma mater since you conducted your PhD here. Yep. Also at the electrical engineering faculty at the IAEW. So welcome. And last but not least is Andreas Ulbig from RWTH Aachen. Welcome on stage. Yes, and Andreas is my boss. He's full professor at the IAW at RWTH Aachen, and he holds the chair for active energy distribution grids. And concurrently, he holds also a position at the Fraunhofer Center for Digital Energy, which combines the competences at the Fraunhofer Institute for Applied Informatics and RWTH Aachen University at the interface between IT and energy technology. He's also co-founder and was for many years COO of the ETH Zurich spin-off Electricity, which developed tools for distribution grid operation and planning. Previous workstations were mainly in France at RTE, the transmission system operator, and the International Energy Agency in Paris. And he comes from Switzerland with his PhD, so he conducted his PhD in the Power System Lab at ETH Zurich. Welcome, Andreas.
Thanks.
So I hope you feel comfortable on stage. And I hope you also look forward, like I do, to this discussion. And yeah, let us first look at the building level, because we're now talking about the transformation of the energy system. And we also heard that there are major technologies which will be deployed there, battery storages, heat pumps, and so on. And there will be manifold technologies. And the first question goes to you, Andreas. Mm-hmm. You've been working at the IEA, and you have overlooked those developments within being part of the World Energy Outlook, which is published periodically by the IEA. And we've seen radical changes in these energy systems. Looking at the building scale, what do you think? What is the major change in the systems? Is it on the heating side? Is it EV?
Yeah, certainly on the heating side. So EVs are also coming in, but changing the heat supply from fossil fuels to electricity is the major change. And as we just learned from Professor Müller, heat pumps on average have a good working efficiency, but not if it's very cold, which is then a problem for the grid because it's cold for everyone, and then we have this peak load demand that the grid will have a tough time to handle. So this electrification is really a game changer. If we look at buildings overall, they become terribly efficient in a positive sense, but from the point of the electricity grid, they will be much higher consumers of electricity than they were in the past due to that electrification of heat.
Quite crucial is what we heard, the simultaneity factor of sector coupling. Adam, I mean, you look at from the grid view. What are the possibilities to look at simultaneity, and how could we cope with these problems on a building scale?
So, we are confronted with this high demand in winter time at 18, 19 o'clock. So what we need really to shift this load, this additional load by EVs, heat pumps, and so on to other periods. So and for this we need this flexibility of the buildings, as well as a possibility to get this, more or less, the energy what we need and don't need at one time to get it in by sector coupling or something else, and to utilize our system not only or the high utilization of the system not only in the evening peak load, then to transfer it to other points in the day.
Thank you. Yeah. So, I mean, there are quite more technologies if we look at flexibility potential. And one major point, which also Professor Moser showed, were battery storage systems. Is there a special role for battery storage systems in our overall system? Is there the need? What is your opinion? And whoever wants to answer that question.
Yes, storage. It's the most important thing for shifting of this peak load to other periods in the day. Yes, this will be also the game changer.
Mm-hmm. Yeah, maybe it's not just electricity storage, but also heat storage. Yeah? So latent heat storage, water tanks, for instance, or something more sophisticated might play a role in actually breaking these peak situations during the winter time in order to enhance the storage capability that the building envelope already has by some additional storage elements in order to reduce the peaks.
I mean, we have now looked at the technical point of it. There is more to it, and that is the question to you, Alex. You looked at IoT systems to digitization. I mean, that will be the enabler in the future to tap this potential. Are our buildings ready to cope with all those with all the technologies deployed? They are hybrid energy systems, you could say.
Yes, I think this technology is very promising. So for flexibility, for congestion management, and IoT and digitalization at the edge of the grid is actually the key enabler here. And one very good, let's say, it could be extremely important for distribution network operators to seize this opportunity to really become a distribution system operator. So from a DNO to a DSO, where I've seen on your slide there, the system is not top-down anymore. You have reverse flows and everything. And the distribution network operators currently don't have much visibility in the low-voltage networks, going beyond the smart meter. And IoT can enable all these flexibility services.
So your opinion is that really IoT is necessary?
I believe so, because let's think of smart metering. It's already here for quite a while, and my opinion is how smart is a smart meter? It's in the end a meter with a modem and a SIM card that communicates data with, I don't know, 30-minute granularity. But vendors like Siemens provide great solutions for the secondary substations, for the DNOs. Yeah, there's a lot of sensors. We've also seen from one of the speakers, you don't even need to put sensors everywhere. You can estimate. And then you have fiber to the building. You have high-speed routers at home. And then if you have your heat pump, your EV charger, your PV on the rooftop of your house with a smart inverter, they all communicate data. So this is where we can leverage IoT.
Yes, thank you. There's probably more than the technologies, the actuators and smart meters to the energy system. It's all about data, and we've heard that quite often. Probably a question to you, Andreas. What is necessary for, we've heard data platforms, probably protocols, to enable all this flexibility in the system?
Well, on a high level, measuring information, so having data is the first thing. Sharing data between stakeholders is then the trickier part. So often regulation comes in the way and is hindering innovation there. So Germany is a good example when it comes to whether or not smart meter data can actually be used by anyone. But that has to be overcome, right? And you just said, Alex, so we have fiber to the home, and the heat pump probably has a larger bandwidth than modern smart meters have. Yeah, so they could measure, or they can, with their hardware, measure it in sub-second intervals, but they typically communicate every 15 minutes or so, if at all. And so there is a lot of improvement that is actually beyond technology, but it's really about laws, regulation, and making sure that the owners of the different measurement equipments can actually work together in a meaningful way to make the most out of the data for optimized operation of buildings and so on.
One more aspect could be that there is interoperability of systems. We have a lot of vendors in the field, and probably not every heat pump does speak the same language. Adam, what is your opinion on that standardization of those things? Are there ongoing activities you have in mind?
Yes, this is a good point. Nowadays, for example, I will just change the topic with the data. For example, the planning departments so I'm consultant, so this is also the point. What we see by utilities, they get the data from GIS, SAP, and so on and so on. And also, if you have also the same vendors, it doesn't mean that you will get the same quality of the data from these systems. So so in this way, it's so important to get some coupling translators in this way to include them to my platform, on the one side to observe my system, but also on the other side to give the impulse for control the units, the buildings, and you have to do it automatically. You do not have anyone by DSO or TCO or someone else who can manage that. You don't have this manpower already nowadays, and in the future less than today.
So it will be a more and more automated system, and who does it overlook is the question. Are there vulnerabilities in the system? Looking at cyber attacks, for instance. I mean, that is the point to you, Alex, I guess.
Well, I wouldn't want to be too negative, say, oh, but cybersecurity. So first of all, I think digitalization should be widely embraced, even by the DNOs, who are quite conservative. It provides lots of advantages, and it has to be done responsibly. So when you go for a tender, cybersecurity has to be part of the tender, whatever they are purchasing, and it has to be also not at the end of the technical specification, but maybe play an important role, because the attack surface is quite broad at the edge of the grid. Just think of, we get solar PV on the rooftop of your house, yeah? And they come with inverters, and now they may be smart inverters. And then you have EV charging with IoT capabilities, so machine-to-machine communications. Now, the question would be, where do you get this firmware? They can be produced anywhere in the world, the devices, and then who is rolling out the firmware and considering the security updates? And how do you know they don't have backdoors and somebody cannot control aggregated volumes of EV charging points or PV inverters? So this is where people have to be a bit cautious and considerate, especially in the tenders.
Yeah, in Germany, or?
Yeah, I mean, I would add, I mean, of course we need security standards, but, you know, thinking about cybersecurity as a risk is good. Having standards for avoiding that as well. Is there a guarantee? No, right? There can always be an attack everywhere. So we should still try to find a good balance between enabling functionalities for a smarter, more intelligent grid operation and still, you know, having the relevant barriers against cyber attacks, but not just one or the other. Yeah.
Exactly. And one example is in the Netherlands, for example, we don't, the smart meters don't have that switch enabled. So if somebody doesn't pay the electricity bill, they won't be able to remotely disconnect the household. And this was, I think, based on a risk assessment, and all the smart meters, they don't have the switching capability. So I'm not saying it's good or bad, but you are completely right.
Okay, that's actually interesting, because I thought initially that was the business case of smart meters, to actually be able to enforce billing.
Yeah, not in Netherlands.
Yeah, but I mean, there's this example of Germany. We're looking at smart meter rollout, and every other country in Europe right now has rollout, because we thought it from the beginning, and it was a big burden. So probably we're in the middle of your discussion here when we look at Germany. Yeah, let's tap one further question I have in mind, and we came up with markets, and it's a quite provocative question. Do we need markets for flexibility coordination? Is it necessary for the system if we look at system-wide grid flexibility, so not only for distribution systems, but also for the transmission systems? Is it still necessary, and what role will it play probably in a distributed system where on the distribution level it wasn't before?
Yes, in my opinion, yes, we need it. We have to avoid to waste the generated renewable energy. So we have to bring them to the market, to the customers, and we need this impulse to get higher or less consumption and at this time. And this is important for the standard operation in a system. If we are talking about critical operation points of view. For example, we lose a lot of load or generation. Then we will need also some signal to our buildings or to flexible loads to get our system into right operating level.
We've seen that market signals could also cause a lot of simultaneity in the system. So we're back at the point, what is with simultaneity? So do the markets work as they are now implemented for a distributed or more decentralized system?
Maybe some remark on that. Yeah, so avoiding simultaneity would be the goal. Yeah, so too much simultaneity means too high peaks, either in production or on load. And I mean, we have cases where tariff-based price signals can create peaks where there were none before. So France is a good example. When the whole country switches from day tariff to night tariff, where electricity then costs half of what it does during the day, then you see an artificial peak of a couple of gigawatts in hot water boilers. Yeah, so that looks funny on a Sunday, yeah, where that artificial peak is not overloading the system, but it doesn't look so funny on a cold winter day in January. And so So we need to have price signals that are designed in a way that we do not create peaks where they weren't before, and actually really, well, ideally bring guarantees in smoothing out load demand and peak production.
Okay, I mean, we've heard already today there are new business models occurring, like energy communities, energy sharing, which could provide that, but probably it's a more local view on that. Are there more business models you have in mind, or do you think of more than a system where the grid operator directly does have access to these things, and then probably it's more a legal issue than a real market issue?
For example, if you are looking at a low voltage grid, so then you have, as a distribution system operator, you have to observe also your equipment. Do I have some overloading or not of transformer or lines in my network? So and then in this point of view, the system operator also will need some signals to reduce, for example, the load at this time, or also increase, depend on the situation in the grid.
There was this quite interesting press article today where it said that Transnet BW, they tried an app right now to the end customers, and they're telling them how far are we away from the blackout. And today was the thing that they said, okay, there will be in 1 hour a red signal because we are not far away from it. So please don't use so much energy. Is it the right way?
To play with the fury.
Yeah. Well, again, the example of France, in France, such apps or app-like messages, earlier days via SMS, that has been around for 20 years. Well, maybe people are frightened, but statistically it's very effective. Yeah? So you can show that peak demand does reduce because obviously the incentives are right. Yeah? So if you hear about a blackout in an hour, probably you reduce your consumption to avoid that. But I think there are smarter ways in doing this. Yeah? So ideally, the machines could organize between themselves how, who has the most flexibility and the least customer inconvenience if peak demand is reduced without having such threatening messages on your mobile phones. Yeah, so I think that's the future, having more machine-to-machine interaction and less worrying on the human level.
I mean, it was a drastic example, but yeah, you can see how far we are in our mindset probably also in this topic. Yes, so thank you. I think we're also at the end of this panel discussion here on stage. And before we start with the question round, I would ask you to make an end statement. So, I mean, what we have in common is we're working in our day-to-day life and our work on the same goal for sustainable energy systems. And there are a lot of challenges we already talked about here. And we heard also today from Professor Brettel that challenges can also be chances for future generations, for our research. So, and especially from the viewpoint of an engineer, what is your opinion? What is the major challenge we should tackle first? Also as a motivation probably to our students here at RWTH Aachen, which you have in your day-to-day business, what is quite urgent?
Okay.
Yeah, if you want to start.
Sure. So as an end statement, yeah. So I would say that distribution system operators or DNOs should embrace digitalization, especially IoT, and should not be afraid of substation in the cloud, any cloud actually, and should not stop just at giving a connection to a household, but should also try to leverage the data that we get via machine to machine to enable flexibility and keeping the lights on.
Thank you.
For the distribution system operators, also the same, to observe to have the observation of their own network, also to build this network into calculation tools and use this predictive point of view to find bottlenecks in the network, and with this observation to use the flexibility of the buildings as well as residential units to avoid overloadings and to increase the utilization of the network.
Thank you.
Yeah, so same message. The innovation is really to shed light into the distribution grids, get from the black box to a whiter box. Maybe not full visibility, but more than today. However, I'm afraid, I know that means a lot of large IT and IoT projects. So IT projects and companies usually create fears and risks because often they go wrong. So maybe you also need to find ways in managing better the complexity of such large digitization and IT projects, and this is what I would hope for. Yeah.
Thank you very much for your last statement, and then we will open the discussion here. So you're free to ask questions. Professor Moser.
Maybe it's not a question, more describing in a little bit more pessimistic way what I observe. Yeah, if I look at the title, how can buildings and grid interact intelligently? Looking at a German situation, no smart meter rollout, no fiber to the house. At least I don't have, and I know a lot of areas that don't have. Flat rates in the retail market. All the things are still like the old world. Technology, to my opinion, is not the problem. Obviously, there are some other obstacles to overcome. What are the obstacles?
I guess this question goes to you. To me.
Well, I can start. Regulation, obviously. Yeah, so regulation is a problem. And also investment incentives, fiber to the home. So apparently telecom and other companies don't think it's a business case. So that's different in other countries. I know that from the Netherlands, in Switzerland as well. So there's actually grid operators who are pushing fiber to the home because they already have the cables and the electricians to install that. So it's the local DSO that installs also the optical fibers. Actually, often the optical fiber comes out of the power socket, because it's the same channel that is used for laying it. So I would hope for more there, because technology is often really not the obstacle. It's there, but it's not deployed, like the smart meters.
Maybe to add up a question, is it also our ambition towards carbon net neutrality?
So, well, maybe this business case, our all decisions, the point is what does it mean to my pocket? So and if it's something as a use case for telecom or someone else, if there is not, for example, they have also to pay the connection, the internet connection in this business case. doesn't count any longer. So and then you have to say, okay, every household has some connections, and all it's on the top. All the communication with the buildings, with the households, and so on, and this will be free of charge. So then, in this point, maybe it will be in this case one business case.
Maybe one thing to add. So on top of regulation, would be various stakeholders joining forces. You have the DNOs, you have the original equipment manufacturers or vendors, municipalities, and I'm not pessimistic, I'm actually quite optimistic, because even things will happen. Imagine we are still on a green field with EV charging. Yeah? So when we think of the next 10, 20 years, we have to replace all fuel cars with EVs. Then you will have IoT-enabled EV charging points everywhere. So then you will have the communications, you will have aggregators and system operators. Perhaps it will take some time, maybe not tomorrow, but I think things will happen.
I hope the answers satisfied you, Professor Moser. You still look a bit skeptical, but maybe we can continue discussion later. Professor Müller has one more question. Okay.
Yeah, after being so negative on this issue, I have to mention something positive. And for example, when we look at the development of the heat pump market, for 20 years we have been waiting for a strong market development, and now it's actually happening. And it's not reversible anymore. So all companies now switching technology, and this will implement this technology in a very fast speed. Nobody has on his paper like 2 years ago. So there's some advantage and some progress. But on the other hand, you mentioned regulation as one of the big issues, making inventions going to practice sometimes very, very difficult. But from my point of view, it's not a problem with politics. The problem starts between companies, because a grid operation company can have a very different interest, for example, from someone who wants to sell flexibility from a building. So how can we solve this issue, that we have a more reasonable influence on regulation by all companies who are involved in this market?
Yeah, good point. I think, well, one important question is to define who owns the flexibility. Yeah, so if you have a heat pump, so it can change at set points, so there's flexibility physically. If the building envelope is a buffer, but who owns it? So in the past, often the grid operators just assumed, they control it. And the sort of idea was to provide some sort of preferential tariff for using that flexibility. But maybe the actual payment to the end customers wasn't really what the flexibility was worth. So changing that in legal fine print, saying, the flexibility belongs to the end customer, I think this changes things, because then you could go the next stage and say, end customers are allowed to aggregate the flexibility and give it to some third party, which is not the grid operator, is not blocked by the grid operator, isn't blocked by the grid regulator, but can actually do something with it. I think this is how we can make it in, so to say, in a user-centric way, push things from the bottom towards the higher levels. Yeah.
Question by Professor.
But maybe not.
So well, if we, sorry.
Okay.
Please finish first.
No, so well, I think we need also this direct channel between distribution system operator and the buildings, but only in the point of view if it's critical operation status of the network here.
Now, as a civil engineer, I would like to bring another point into the game. Now, I think it's our German mentality that we sometimes think in black and white, and that we forget that the transition is a very colorful piece. And we know that that especially the refurbishment issue is a major point. So if we have heard about the peak load problem. So if we now switch all to electricity, all to heat pumps, etc. So then we run into a serious peak load problem. But on the other hand, we have a 90% refurbishment problem. That means we have existing technology like combustion issues, etc. So if I now look to the market and I ask, is there a hybrid system available where I can maintain my existing system as a peak load system, which then perhaps will operate in the future only by 20%, and I buy a heat pump system that then can be operated in the range where it really likes to be operated and not within the peak load area. But how about such hybrid systems on the market and the availability? How do you see that?
So I can't say much about market availability, but such hybrid systems typically offer more flexibility because, right, you have different working and operations ranges that you can work in, so that provides flexibility. Yeah. So shifting between fuels also is providing more resilience. So we see that in Germany, even in a cold winter, we are typically not running into situations where we see blackouts, whereas France, who is fully reliant on electricity for heating, structurally has this problem no matter what they're doing. So having more fuels, multi-energy systems by nature provides more resilience to, in particular, unforeseen disturbances.
I agree, but my point was more that if I want to buy a hybrid system, simply systems can't talk to each other. That's not an open standard available. That an old system can talk to a new system. Yeah, is there a Modbus available, or is there a bus system available at all? Yeah.
Yeah, well, we had this point early on that we have different communication protocols and standards, and well, the vision should be to have maybe not one protocol, maybe that's not necessary, but having protocols that are open enough that different machines can interact with each other, that I can write converters for exchanging messages between old and new systems. That would be needed. And very often in the energy industry, we have closed formats for grid models, for instance, which is very much hindering innovation. And that is only slowly changing, and that could need a push from the regulator to actually, on a very high level, ask for common standards that are readable and are not blocking innovation because they are closed. Yeah.
Question before we finish the panel discussion. Then we can wrap it up.
Okay.
Yes?
So, yeah, we've heard a lot of discussions on this topic, and I'm very happy that you as an audience also came up with some questions we could discuss here. And yeah, thank you once again, you three, for the lively discussions and all those inspiring things. And we heard that the ecosystem here is quite lively with TU Delft, Siemens, and RWTH Aachen, and I'm looking forward to networking with you and thinking a bit more about the challenges and how we can tackle them together. So thank you very much. Have a nice day. Thank you. Continue.
Thank you so much. I would kindly ask you to take your seats again. Thank you, Niels. Thank you so much for the interesting and lively discussion as Niels wrapped it up. So before we close the first day of the conference, I would like to hand over to Dr. Peter Körte again for the official wrap-up and, of course, also the announcement of the winning pitch.
Cool.
Thank you.
First off, a big thank you to everyone who contributed to today's conversation. This was really great. Now, of course, for the three PhD students, well done. I have to tell you, I mean, nobody liked to be fried in front of everybody in 3 minutes, and this is tough. So all of you did really, really well. However, we had to choose one of you who is the winner, and I think Natasha. So Natasha Eckert, she's the head of university relations at Siemens. She's also the head of the PhD network, so she knows how you feel. And Natasha, therefore, why don't you come up and you share?
Yeah, I do.
You share with us. Yeah, actually, sorry for that. You share with us. I think there was a tight race, and
absolutely,
absolutely.
We were also not only the presenters were under pressure. I think also the jury was. It was a speedy decision, so no discussion. I think. I hope we had a joint decision. I'm also the sponsor of the award, so I'm really proud to be here. And now I think we tell them what it is.
You think so?
So the 3,000 euros goes to Philipp Stoffel. So congratulations, Philip. Yeah. It's all for you. Hope it warms up a bit your cold winter here. For me, it was a bit a selfish decision because my office is located southwest, and on a sunny day, it's so hot. And right now we have a energy reduction at Siemens to 19
like
degrees,
so
19
like
degrees, and when it's snowy outside, it's really, especially if you don't move, it's pretty cold. But as soon as the sun shows up, it's getting warm. I open up the window, and I think that's a waste of energy.
Yeah,
so
that can be automated.
Hopefully soon. When have you finished your? Will you have finished the?
Depends on him, but hopefully in 1 year and a half.
I think we need some more. We need some more money to speed up the PhD. Okay, so congratulations.
Yeah,
Philip.
Thanks a lot.
Congratulations.
Thank you.
Very good. I think this really, thank you, Natasha. This really concludes our first day. Super delighted that we are talking about such an important topic. Let me share with you a story just 2 weeks ago that happened, and I think many of you didn't know. But so EV charging, right? So 18% of all the CO2 emissions globally are linked to transportation. So obviously we need to switch to electricity. So therefore all the generation, all the distribution, everything that comes with it. Now for that you need to have fast chargers and home chargers and whatnot. But in particular fast chargers are interesting because you need to have billing. And for the billing you need to have authentication. For authentication you need to have communication. And for communication you need to have mobile networks. So all the charging networks in Germany are using one specific mobile network provider. That very day, 2 weeks ago, that mobile network provider was down. As a matter of fact, nobody realized that the SIM cards that were being used were actually locked down, and thereby all the manufacturers, including ours, but many others too, EV charging stations didn't work properly. Yeah? And so it took almost 24 hours to rectify. It gives you a little bit of a glimpse of what we're heading into, because I think actually electricity becomes a very critical infrastructure, and EV charging becomes a very critical infrastructure. So there's many challenges that are ahead of us. That said though, and that was the conversation that we just had on the sidelines, is I personally believe all the technology, the basic technology that we need is there. If you think about cost competitive renewable energy generation, we've been waiting for this for decades. It is there. If you think about HVDC networks, well, they're there, but we have to build them though. If you think about smart meters, which we discussed about, they are there for many, many, many years. Smart building controllers, what have you. And also, by the way, the mathematical models and of course, what you talked about. If we put this all together, is really the key thing. So I always, when I listen to all of you, I always wonder, where do we start? In other words, also the question about if you had one magic wand that you could wave, what is it that we would be looking for? Because as far as I'm concerned, the technology is there. We just have to make it, applied and get it going. And last point on this one is 19 degrees. So here we are. So maybe I always was wondering, are we just, happy enough and everything is good enough? And so therefore there's just no catalyst for change. So the infamous burning platform. As a matter of fact, I think we have a cooling platform right now. And so we definitely need to have really, when, if not now, we would start changing and think about how to make this energy transition work. Because this chance almost is unprecedented and we really should be using it. So as you are heading out tonight, maybe you can also think about how can we really accelerate, how can you personally make a change. I'm trying that as well. We had the discussion this morning as well, is how do we accelerate this transition? The time is now, because if you think also for many, many years, many of the transitions didn't make sense economically. Well, they're not going to get any better. So right now, probably the best time to do this as we speak is right now, let alone the whole security of energy for sure. So with that, I leave that with you, really thinking about what can we do, what is it that we need to do. I don't have the answer either, but I hope that we can continue the conversation also as we have a little bit of a get together. And with that, I hand this over to Professor Rüdiger, who's joined us, and thank you for taking the time out of a very busy schedule. I know this was important to you, and so thank you for taking those minutes and with us for tonight.
Yeah. Thank you so much for the floor. And now we have two options. So I prepared a few words for wrap up.
Yeah.
We can do this right now and here. The other option is we grab a drink over there and then I deliver a few words in front of the buffet. Yeah. So maybe the second option is the more favored option.
So option one, option two.
Great, I think decision is made, but before we all move next to the official closing words and also for the dinner part and the networking, I just want to officially close the first day. As I said, it's just the first day. Thank you for joining us here in person as well as online, being part of the conference. We have a second day, so it's not over for everyone who came all the way from different parts of Germany. I hope you're staying also for tomorrow and join our expert exchanges, the lab tour that we are organizing at the IAEW Institute, and also the tech talks, do you still have my... No. Maybe you. Oh, I did. Oh, yeah. I was like, I remember handing it over to you. All good. But, oh, yeah, perfect. My great colleague was faster than me. Thank you, Christina. But, yeah, so I hope that you will join us either in person tomorrow at the Collective Incubator, where we continue the second part of the conference with the tech talks, the expert exchanges. So we're going to keep talking about the grids and building technologies that we had the discussion here over there, and even discuss further on the topics within small groups. And as I mentioned, the tech talks and the Young Innovator panel. So I'm looking forward to that part. And our online guests are also able to join us for the tech talks and the Young Innovator panel. Now, if you have any questions about what we are doing here, or about the conference, about Siemens, the university, feel free to get in touch with us. Also at our RWTH Innovation, our mission is to bring the academic world together with the industry as we're doing it today and to enable collaboration. So if you have any questions on that, feel free to contact us. You can scan the code, you can talk to us later. And of course, I would be very glad to see you tomorrow again. And I want to officially close and invite you all to move next to the dining and networking area. And first, we're going to have the closing words from our rector, Professor Rüdiger, and then we can dine and talk. Thank you all for being here and joining. Thank you.